Thank you very much. So again, I have lecture notes on my website, and also both slides from yesterday and the slides from today are available there. Uh, it's likely tomorrow I'm going to use the whiteboard, so probably there's not going to be a slide 3. But I just want to start with the same question that I asked yesterday. Where are we and where are we going? So by now, actually, it's great. It was great to hear that we essentially covered everything on the bottom. So we know about equivariant, we know about cohomology, we know about K-theory. We've seen equivariant cohomology, and we've also seen equivariant K-theory. So now we're gonna go one step upwards. We're gonna add a Q to everything. And again, please remember the story that I said yesterday. So quantum K-theory is essentially like K-theory, so it's not a graded algebra, it's a filtered algebra. And so you're going to have some extra terms which have degree more than they should have. And those are exactly the quantum K terms. So if you look, again, just to remind you, if you look at the left-hand side here, it has degree 12, 3 plus 2 plus 1 times 2. You work in quantum K-theory, so the Q has a degree of Q is 6. And then just look at the terms which have more, which have degree 12 or more. So the first term here is Q squared. This has degree exactly 12. And there is a blue term here, which is 2Q squared all 1. This has degree 13. 13 minus 12 is 1. 1 is an odd number, and therefore you have a minus sign. Here you have degree 14. 14 minus 12 is 2. 2 is an even number, and you see a sign of plus 2. So perhaps it's not surprising that this is related to the positivity that was mentioned at least in 2 lectures so far. And I'm going to mention there is a positivity in quantum cohomology, there is a positivity in quantum K-theory, and also in equivariant quantum K-theory. It doesn't mean that all these positivities are actually proved. So there are some of the statements are proved, some of the statements are still conjectural. So so today, and again, this very nice calculation, just go on Anders' webpage and you're going to find this beautiful program, and it can easily spit out any calculation that you want for quantum anything for co-minuscule Grassmannian. So my goal for today is really to tell you what quantum K-theory is, and later on I'm going to tell you about the quantum K pairing. And then my goal for tomorrow is to tell you how to actually calculate quantum K-theory for the Grassmannians. So let me start by saying what quantum K-theory is. So quantum K-theory, so we're going to take G mod P, our usual partial flag manifold, and quantum K-theory uses some additional set of parameters. These parameters are indexed by a sequence of Qs, which corresponds to a basis of the second homology group of G mod P. In other words, you have a sequence of parameters which is indexed by the Schubert curves. For the Grassmannian, rank of H lower 2 is 1, so you just have one Schubert curve. Everything else is a multiple of that Schubert curve. But for the full flag manifold, you have FLN, you have n minus 1 Schubert curves, which correspond, if you want, to the simple transpositions in the symmetric group Sn. Okay? Often I'm going to talk about Q to the D, and by that I mean really a Q1 to the D1, QR to the DR, where R is the rank of the H lower 2. And these Ds, of course, they have to do with a multi-degree. So quantum cohomology and also quantum K-theory has to do with curves. These curves have degrees or multi-degrees, and they're going to be encoded in this Q to the Ds. All right, so from the additive point of view, quantum K-theory, it's very simple. It's just a tensor product over Z of the usual K-theory with a power series which depends on this sequence of parameters. So, and if you want to go equivalently, it's the same thing, except that you have to replace this power series, this Z here, by the T equivariant K-theory of a point as we've seen in the previous lecture. So in particular, because the K-theory of the partial flag manifold is a free module over Z, then automatically you have that the quantum K-theory is a free module over this power series ring. So additively, the quantum K-theory is very simple. However, what is interesting here is how do you actually define a multiplication in this free module. So that's going to take us some while. In order to define the multiplication, we need to define this object called Gromov-Witten invariants. The Gromov-Witten invariants have to do with spaces of curves. Quantum cohomology counts curves. In quantum K-theory, you look at a measure of a space of curves, and that measure is defined rigorously as an Euler characteristic, as they usually do in K-theory. So let me go ahead and talk about this Gromov-Witten invariants, but initially I have to talk about the moduli space of stable maps. So this is where the curves are coming from. So let's say that we pick an effective degree. Yes? It's not obvious at all, and I'm going to talk about there is an issue about finiteness. This is actually a serious problem. We're going to see in a moment. So this was a serious problem in the field, and it has been solved, but this was an open question. So we're going to get there. I'm going to explain why this comes up. So okay, so let me talk about the moduli space of stable maps. So the moduli space of stable maps, it's a compactification of the usual maps. So what you want to do is you want to look at maps from P1 to your space, just morphisms from P1 to your space of a particular degree. Let's say that you fix the degree. The degree means that if you push forward the fundamental class of P1, you get that degree. And I think in Frank Sotili's lecture at the very end, you could associate degrees with chorus, things like this. So a degree is really an element in the second homology of this G mod P. It's a combination of Schubert curves. Okay? So what happens is that you want to consider all these maps at the same time for a fixed degree. The problem is that this space is not compact. So you need to compactify it. There are several ways to compactify the space of maps from P1 to G mod P of a fixed degree. One particular way to compactify is this moduli space of stable maps that was introduced by Kontsevich 1993-ish. So which is particularly good for the definition of the quantum cohomology, also quantum K-theory. But before I move on, I should say that there are some other ways to compactify spaces of curves. There are things called quasi-maps. I'm not going to talk about those, but I'm just going to throw some names just in case you hear them later. So there are things like quasi-maps, there are quote schemes, and other things, Drinfeld moduli spaces, and so on. The point is that you can try to define a similar theory for these other spaces, and currently there are some questions in the field of whether the theories really coincide. So for now, I'm just going to focus on the moduli space of stable maps. As I said, this compactifies just maps from P1 to G mod P of a fixed degree. And what are the objects? Well, an object in this moduli space is a map. So how do you compactify it, right? So is a map from a rational curve C. This C here is just a tree of P1s. And this rational curve has some marked points on it, which have to satisfy some conditions, which I'm not going to get into. But the map is a map of degree D. So if you push forward the fundamental class of C, then you get the specified degree. And these marked points on the curve are used to define evaluation maps. So you can define an evaluation map from this moduli space of stable maps 2x, which sends such a curve to the evaluation of the curve at the ith mark point. So for example, if you take 3 mark points and d is equal to 0, then m0n x0 is just x. So there's nothing to do. And all the evaluation maps are just identity maps. So I'm not going to use these properties today. I mean, they are implicitly used in what? So we're going to live in paradise today, so everything is true. But really behind some statements that I'm going to make, there are some statements about the geometry of this moduli space of stable maps. And some of the statements are here. So first of all, this moduli space of stable maps is a projective variety, and it's almost smooth. It's almost smooth. It's not quite smooth. Has so-called finite quotient singularities, and it has also so-called rational singularities. So these are the type of singularities which are really good for cohomological calculations. I should say, without defining what rational singularities are, that if you have a variety with rational singularities from a cohomological point of view, it behaves like a smooth variety almost. Okay? It's also for moduli spaces of stable maps are also connected and also irreducible varieties, and they're also rational varieties. Rational means that there exists a big open set in this moduli space, which is isomorphic to a big open set in AN, in the affine space. Okay, so it's birational to Pn if you want, for some projective variety. So these come up when you actually calculate invariance. Let me now define Gromov-Witten invariance. So now we're going to use this modular space of stable maps, and we're going to use the evaluation maps. So let's say that you pick n classes in the K-theory of X. And let's say that you fix a degree. Then I'm going to define a quantity. This is going to be a number. This bracket A1, AN, D. So you define a number in the following way. Well, you pull back these classes, A1 and so on. You pull them back to the moduli space. These are going to be K-theory. These are going to be classes in the K-theory of the moduli space. You multiply the classes there, and then you take the Euler characteristic. So remember this, yes? So remember that this integral just means taking the Euler characteristic in K-theory. And I should say that exactly the same definition works in cohomology or in K-theory, except that in cohomology, the integral means push, well, both in cohomology and K-theory, the integral means push forward to the point, but in cohomology, because of the degree condition, many of these products will be zero if they, you need some degree, you need that the degrees of these classes add up to the dimension of the moduli space. Otherwise, this integral is going to be zero automatically in cohomology. In K-theory, things may not be zero. So in cohomology, this integral, there is a statement. This integral is just counting curves. It counts rational curves. So you should think of this. Oops. See? Okay. So you should think of this Gromov-Witten invariant as counting rational curves from C to G mod P, with the property that f of the first point belongs to the class A1, f of the second point belongs to the class A2, and so on. So you think of the classes A1, A2 as classes associated to some subvarieties. In cohomology, you would count such curves, and if you have infinitely many curves, then the integral is zero. In K-theory, you look at the measure of the space of such curves. So you might have a positive dimensional space. You're just looking at all the curves that pass through these cycles, and you take the Euler characteristic of that space. All right, so there is a technical condition here about the moduli space not being smooth, but as I said, it's almost smooth. It has rational singularities. Now, we want to define a product. So how do we define a product? This in fact, was the definition of the quantum cohomology product from the very beginning. You're defining using a pairing. In all these situations that we've seen, in particular in the lecture in the morning, Dave's lecture in the morning, we've seen that the pairing plays a very important role. So all these spaces that we're looking at, they come with pairings. And then once you have a pairing, you can ask several things about it. But one thing you can ask is you can try to define a product using the pairing. This is called a Frobenius property. So you can try to define something like, well, if I have a perfect pairing on a space, I can try to define a product of two classes in a unique way so that it pairs with a third class in a specified way. Okay? So now I'm going to define a pairing in quantum, the corresponding pairing in quantum K-theory. So the pairing is defined in the following way. So you pick two classes. and then you want to define this double bracket pairing. So this is the usual pairing. So this is the first part of the pairing is this 0. This is the usual pairing in K-theory. And then you have to add an infinite, a generating series of all the 2-point Gromov-Witten invariants corresponding to the classes A and B. And you put this Q to the D, right? This is the bookkeeping device. In particular, this is an honest power series. So this is an honest power series. If I would do this in quantum cohomology, it would turn out that only one term would survive there because of the degree reasons, because the quantum cohomology is graded. And I don't need the pairing. It's just the usual Poincare pairing in that situation. But in quantum K-theory, we need a deformed pairing. And then using this pairing, so one can prove that, that this pairing is non-degenerate, essentially because the degree 0 part is non-degenerate. And then you define the product in the unique way so that this is satisfied. This Frobenius condition is satisfied. So if you take two classes and if you want to multiply, in order to tell you what is the multiplication of two classes, I'm going to pair it with a third class. And I'm allowing that third class to be general. And I'm telling you that the pairing of A times B comma C is the sum of A, B, C, D, Q to the D. So so this encodes the 3-point Gromov-Witten invariance. So in other words, to define products here in quantum K-theory, we'll need both the 2-point, we'll need to know both the 2-point invariance and the 3-point invariance. Okay? So let me actually do some examples. So here so now we're gonna live in paradise for the moment. So so let me just calculate what is the pairing of 1, 1. 1 being the structure shift on G mod P. So this is just OX. Well, by definition, this is just the usual pairing, 1, 1, plus the sum when D is larger than 0. And I'm putting here a 2-point invariant corresponding to 1, 1, and then this is a Q to the D. And because of the rationality and because of the rational singularities of the moduli space, it turns out that all these 2-point invariants are equal to 1. So in fact, as you well know, this is just a geometric series, right? So if I would have a single parameter here, I just get 1 over 1 minus Q. If I have several quantum parameters, it's 1 over 1 minus Q1, 1 minus Q2, and so on. So this is just a geometric series. So this is the pairing of 1, 1. Let's use that definition of the quantum K product to actually calculate what is 1 circle 1. Okay? Well, what do we want to be? We want to be equal to 1, right? So I'm going to put a question mark there. Is 1 times 1 equal to 1? Well, in order to check that 1 times 1 is equal to 1, I have to pair it with an arbitrary class. So I'm going to pair it. So by the definition of the product, this is the sum over D larger or equal than 0 in this case. It's going to be 1, 1, A, D, Q to the D. Right? This was the definition of the product. Okay, now, again, today we live in paradise. So I'm going to cancel one of the ones. This is called the string equation. So I can actually, a 3-point invariant where one of the classes is equal to the identity is equal to the 2-point invariant where I can delete the identity class. Okay? So there is an equality. Each of the 3-point invariants there is equal to each of the 2-point invariants. But of course, now this is just the definition of 1, A. So what we checked here is we checked that 1 times 1, A is equal to 1, A. By the definition of the product, this implies, of course, that 1 circle 1 is equal to 1. So here it is, our first calculation in quantum K theory. The string equation comes into the proving that the invariants behave in the correct way. So it comes in the equality of the 3-point invariance is equal to a 2-point invariance. So you use the fact that that the general curve is rational, and it's essentially a P1, and then you can just push forward that class. So it's going to be a calculation of higher direct image. Just R1 needed in that situation. Okay, so all right, so then we defined something. We don't quite know what we define. We define an operation on this object, but according to Giventhalь and Lee, this is in fact this product. This operation gives the quantum K-theory the structure of a commutative associative ring with identity. Okay, so this is actually an associative algebra. And just right out of the definition, it follows that if you make Q is equal to 0, so in other words, if you mod out by the ideal generated by Q, then you just get the usual K-theory. And again, because K of X was a filtered algebra, if I give a degree to the quantum parameter or to the quantum parameters, this is going to give me a structure of a filtered module on the quantum K-theory. And in fact, it becomes, the quantum K-theory together with that degree of Q becomes a filtered Z of Q algebra. So in other words, if you multiply a class of degree I times a class of degree J, you're going to see perhaps a class of degree I plus J and then some higher order terms. This is what we've seen in slide 1. Okay? So, and then if you take the associated graded of the quantum K-theory of this filtered algebra, then you just recover the quantum cohomology. So that was this fact that if you take the top term, then you get the quantum cohomology. That's the same thing in K-theory, right? If you take the associated graded algebra of K of X, you just recover the cohomology. All right, so so this was a bit abstract, right? I mean, I was defining this product by a pairing, blah, blah. So, but we want to unravel a little bit that product. So what does it really have to do with curves? How do you actually see the Gromov-Witten invariance coming up? So I'm giving you here two formulas. One, it's an easier formula. It's very nice to program it. For example, it's a recursive formula. It gives you a formula for the structure constants in terms of like smaller structure constants. And the other formula has all the 3-point and 2-point Gromov-Witten invariants coming up at the same time. So it's perhaps harder to swallow, but it's good in geometric applications. So let me talk a little bit about those. So as we said, K-theory is a free module. Therefore, quantum K-theory is a free module. So let's multiply two classes together. So I'm going to multiply the class of one Schubert variety with a class of some other Schubert variety. I expand that in terms of the Schubert classes. And then I get some structure constants. And I'm interested in writing down precise formulas for this structure constant. So this is what these two formulas give. So the first formula says that the structure constant for U, V, W, and D can be written as a Gromov-Witten invariant. So notice here that I'm pairing two classes and the dual of the third. This is what Dave was explaining just in the lecture before. So two classes times the dual of the third. And then I have some correction term. So this is a correction term. Correction. The correction term depends on structure constants which have strictly smaller degree. So I'm adding here over strictly positive things. So D minus D prime is strictly smaller than D. So I have some structure constants which are recursively known, and I also have some 2-point invariants. So you can see from this first formula that a particular structure constant, to calculate a particular structure constant, it requires a lot of information. You need to know 3-point invariants and 2-point invariants, and lots of them. You need to know one 3-point invariant, some recursive procedure, plus lots of 2-point invariants. By the way, since this is an aside, if I would only do quantum cohomology, this correction goes away. In quantum cohomology, you only have that term surviving, for degree reasons essentially. I'm not getting into in there, but only that part survives. So that would be the definition of the structure constants in quantum cohomology. So okay, so today, just as a preview, I'm going to focus on calculating the 2-point invariance, and tomorrow I'm going to focus on calculating the 3-point invariance. So today, hopefully, at the end of the day, you'll know how to do this for any G mod P, and tomorrow, hopefully, by the end of the day, you'll know how to do this for Grassmannians. Okay, so this is the first formula. Now, if you unravel this formula further, because this is a recursive formula, then you get this ugly-looking sum. So you get the same term as the first here. It's a 3-point invariant. And this part here unravels as a 3-point invariant multiplied by many 2-point invariants. Okay, so you kind of have to do this over and over again. The point here is that the degrees here all add up to the total degree, the degree d. So this d0, d1, ds all add up to the total degree, and all these di's here are strictly positive. All right, so we're going to move towards understanding this 2-point invariance. But before I do that, let me just give you a preview of what do we know. And of course, this is absolutely an incomplete list, but it's what do we know from my point of view on the Grassmannian side, from the point of view of these lectures, let me say. Okay? So what do we know? So some theorems about quantum K theory of G mod P. Well, we know how to calculate the quantum K metric. So if you give me any two classes, here I'm giving a formula for like how you pair a Schubert class by a dual Schubert class. And I'm telling you that this is always 0 or 1. It is 0 or 1, but there is a little thing here called this U of D. So this U of D is an element of in the Val group, in the associated Val group of G mod P. This U of D actually is a Val group element that indexes a Schubert variety called the curved neighborhood of the Schubert variety X of U. So I'm gonna define this curved neighborhood later on. So we have a formula for this, and we also have a formula, an easy formula based on this curved neighborhood technique for the pairing. So we know how to pair any two Schubert classes. If you want to pair any two Schubert classes, this is what you do. You quantum multiply them again. You don't do quantum K, you do quantum H multiplication. You look at the minimal quantum degree that comes up in the multiplication of two Schubert classes. You put that on the top. So this is Q to the D mean UV. This is the minimum quantum degree coming up in the multiplication of XU by XV, and then you multiply by the product of 1 minus QI. I'm going to give you an example about this a bit later. So this formula is true for all the G mod P's. It's a theorem. Many of these results were obtained with Anders, Chaput, and Perrin. And the particular theorem in this case was obtained in joint work with Anders, Sjubon, Chang Zhengli, and myself. Okay, so that was the first question, the first theorem. The second theorem is what Dave mentioned, is the finiteness. Remember, I told you at the beginning that if you pair 1 by 1, a 2-point Gromov-Witten invariant, 1, 1, D is equal to 1 for all the D's. So in particular, there is no reason a priori to have the structure constants vanishing for very large D. I keep adding stuff. But somehow, miraculously, things cancel because of the signs and so on. And that was a problem in the field for a while. So the finiteness of quantum K theory has been proved. For Grassmannians, it was proved in maybe 2013-ish, the BCMP, so Anders, Chaput, Perrin, and myself. And then for all the G mod P's, it was proved by Dave in joint work with Linda Chen, Tseng, and Iritani, and also proved by Stu Kato using different methods. So, okay, so we know that the product is finite, although I'm going to keep sticking to my power series. Positivity. So one of the titles of the lecture notes is positivity in equivariant cohomology, equivariant K theory. Well, we also have positivity in quantum K theory. And what can it be? It is what you expect. Once you give Q a degree, then it's the same positivity that happens in K theory. So if you multiply two Schubert classes, O lambda by O mu, and then you expand out in terms of the Schubert classes, then you have this expected difference in degrees, right? So the left-hand side has weight, well, the length, the number of boxes of lambda plus the number of boxes of mu. The right-hand side has number of boxes of nu and the degree of q to the d. If you take the difference between the two, then you get this quantity here. And that quantity, gives you the sign of the structure constant. All right? So we do have positivity. At this moment, positivity is only proved for Grassmannians and more general for minuscule Grassmannians, but is wide open as far as we know for Gmod P's. And finally, I'm going to talk about this tomorrow. So I'm going over this very, very fast. This is a preview of what's going on tomorrow. This is the quantum mechanical classical. So without explaining too much, I'll just say that the idea is the following. You want to calculate some Gromov-Witten invariant on the Grassmannian. It turns out that this calculation can be reduced to an honest invariant on an auxiliary flag, on an auxiliary space, which is in this case, it's a two-step flag manifold. So this is why it's called quantum mechanical classical. You start with something quantum here, and you have some classical object here. And this type of statement is true in equivariant K theory as well, with the caveat that this statement gives you not structure constants, it gives you Gromov-Witten invariants. So to actually get structure constants out of this statement, you'll have to still do that complicated alternating sum, or maybe use the recursive procedure. And this quantum mechanical classical phenomenon has many applications, which I'm not going to be able to talk about in these lectures, but I'll just mention them very quickly. So you can get structural theorems, like how you multiply in quantum K theory. You get presentations by generators and relations for the quantum K ring. Positivity, the proof of positivity is based very much on this quantum mechanical classical, and maybe Anders will talk about the Seidel representation and the combinatorics of the quantum shapes later on in the conference. All right, so I promised you an example about the pairing of two classes. So let's say that I want to pair the class 3 to 1 by 3 to 1. So what should I do? Well, I should do the quantum multiplication of that class. I'm going to give you later on a combinatorial formula for this, but for now I'll just stick to that to the geometric point of view. So if I would do this in quantum K theory, it's a bigger multiplication. You see these like blue terms here. So ignore those if you just want to do quantum cohomology. So if you ignore the blue terms, and if you focus on the black terms, you can see that the minimal power of Q that comes up is Q to the 1. There is a Q to the 1 here, there is a Q to the 1 here and there. So that means that the pairing, the quantum K pairing of O3 to 1 by O3 to 1 is this Q to the 1, and you have the usual denominator 1 minus Q. Okay. So any questions so far? So I guess I'm going to switch to combinatorics from this moment on. I'm going to give you a combinatorial way to calculate this pairing for Grassmannians. Maybe I'm going to talk about full flag manifolds as well, but for Grassmannians we have, in fact, for all flag manifolds we have a combinatorial explicit way to calculate the pairing, and this is based on this notion called curved neighborhoods. So what are these curved neighborhoods? So you start with some closed subvarieties of your Gmod P. And you use the evaluation map to pull them back inside the moduli space. So this will correspond to curves with the property that the first mark point is sent to omega 1, the second mark point is sent to omega 2, and so on. So this corresponds to curves which satisfy some incidence conditions corresponding to these varieties that I'm choosing. These are called the Gromov-Witten varieties because they live in the moduli space. Now what I'm going to do is I'm going to take one of these Gromov-Witten varieties and use one of the evaluation maps to push it forward back into the Gmod P, into the flag manifold. So that's going to be called the curved neighborhood. So the endpoint curved neighborhood of corresponding to this varieties omega 1, omega n is defined as the image to the n plus first evaluation map of the corresponding Gromov-Witten variety. If you want, this is like a correspondence diagram. Let's say that you take n is equal to 1. Perhaps this is the simplest example. So if you take n is equal to 1, then what do you have? You have the moduli space, M02. And this comes with two evaluation maps, EV1 and EV2. Here you have the variety omega. And then what you do is you pull back and push forward. Okay? So the curved neighborhood in this case is going to be gamma d of omega. It's going to be just EV2 of EV1 inverse of omega. I'm going to give you some examples of this. These are actually, they sound maybe a bit fancy at this moment, but we can actually calculate this. We can see what they are. So I'm going to ignore this. You can do this for more fancier moduli spaces when you take like things in the boundary of this moduli space, and you're going to get more complicated curved neighborhood. But let's see some examples of this. So I'm looking at curved neighborhoods, and I want to see, okay, the simplest example is when the degree d is 0. Well, when the degree d is 0, all the evaluation maps are just identity maps. And then this curved neighborhood just recovers, a two-point curved neighborhood just recovers the intersection of the two varieties. Okay? Because you're just looking at all the curves of degree 0, which intersect omega 1 and omega 2. But the curve of degree 0 is just a point. You're just looking at all the points inside omega 1 and omega 2. Yes, thank you. Indeed. I mean, I don't have to, but if I want good behavior, then indeed I want them to be in general position. And in fact, there are transversality statements here saying that if the omegas are in general position, then the Gromov-Witten variety has the expected dimension. It has, well, if omegas also have maybe nice singularities. Yes, that's correct. Yes, that's correct. Yes, thank you. Okay, so the first example was when d is equal to 0. A second example is, let's take d larger than 0, but let's take Pn. So I'm claiming that the curved neighborhood of a point is Pn. Why is that? Yes. So why is that? So well, what are you trying to do? So let's take P2. So you're gonna draw P2, the plane, right? And let's say, oops. So I have a point here. Let's take d is equal to 1. My question is, how far inside P2 you can get from that point with a curve of degree 1? The curve of degree 1, of course, is just a line in P2. So I have a point, and I'm looking at all the lines that pass through this point. How far I can get? Well, I can get anywhere. Because if you give me any other point in P2, there's going to be a line joining that other point with this fixed point. So that says that gamma 1 of a point is P2, is the whole P2 in this case, and in general is the whole Pn. And of course, once gamma 1 is Pn, if I can join any other point by a line, then of course I'm going to be able to join it by a quadric, by a cubic, quartic, and so on. So this says that in fact all the gamma d's, all the curved neighborhoods for points in Pn are equal to Pn. However, if I put two conditions, so if I look at the curved neighborhood, a two-point curved neighborhood where I have two general points here, and I'm looking at the curve of degree d that joins them, well, if the curve that I'm allowed to use only has degree 1, then I get that line that joins the 2 points. But if the curve is more general, then it can pass to anything else. Okay, so any point that I choose in Pn is going to sit on some curve of quadric or more that passes through these 2 points and also passes to that third point. Okay. All right. So what are some properties of these curved neighborhoods? And this is actually related to the previous question. Is that well, if I consider these varieties in general position, then first of all, the Gromov-Witten invariant that corresponds to the structure shifts of these curves is just the Euler characteristic of the Gromov-Witten variety obtained by pulling back these varieties. So a Gromov-Witten invariant is really the measure of the space of curves passing through this omega 1, omega 2, and so on. So this makes this precise. Furthermore, if I only have two conditions that I'm allowed to use, then the Gromov-Witten varieties are always irreducible and they are also rationally connected. So they can, any 2 points can be connected by a chain of rational curves. This is what it means. And in fact, I'm going to focus on the third part. If omega is a Schubert variety, and if I'm looking at the curve neighborhood of a Schubert variety, then that's again Schubert. Why is that? What's the idea of that? Well, remember how that single curve neighborhood was obtained. It was obtained from a correspondence. So if you start with a Schubert variety omega here, a Schubert variety is irreducible and it's stable under a Borel subgroup. If you pull it back, according to these results, again you get something which is irreducible, and because the evaluation maps are equivariant with respect to the larger group G that acts on G mod P, the Gromov-Witten variety is going to be again irreducible and again stable under G. So when you push forward that variety here, which is irreducible and stable under G, of course you're going to get something which is irreducible and stable under the Borel. Under the Borel. So you're going to get something which is irreducible and stable under some Borel subgroup. So that's the definition of a Schubert variety. A Schubert variety is exactly a variety inside the flag manifold which is irreducible and it is stable for some Borel subgroup. So this is why this is always going to be a Schubert variety, this curve neighborhood. So we want to say exactly what it is. We can actually identify, now that you know it's a Schubert variety, you want to say, okay, well, let's say that I start with the Schubert variety XU. What is the curve neighborhood of the Schubert variety XU? Can I identify the value group element that indexes that? If I start with a partition in the Grassmannian, can I say what's the partition corresponding to the curve neighborhood? Things like this. Okay, so first of all, before telling you the answer to that, I'm going to tell you how is that used. So it's used to define these new elements. So knowing that the curve neighborhood of a Schubert variety remains Schubert allows us to define two types of elements. Now it's really important to have like two opposite conventions. Yes. Yes, cohomologically trivial means that the push forward of the structure shift is the structure shift of the image, and the higher direct images are zero. It's a very important technical condition that allows these calculations to actually work in K-theory and not just set theoretically. I'm kind of like, we live in paradise today, so everything is good, but there are actually some serious technical conditions, and one of them is this cohomological triviality. And it's rather complicated when it holds, especially for maps which are not birational. And this is a big theorem of Collard and so on. I will not get into that. No, not in general, no. Those which are birational will contribute to the quantum cohomology Gromov-Witten invariants. And in fact, you can get like easy proofs of the Chevalier formulas in that way. But in general, in quantum K-theory, this map is not going to be birational. Okay, so the fact that we know that curve neighborhoods of Schubert varieties are again Schubert allows us to define two types of elements. I'm going to call them U of D and U of minus D. This U of minus D has to do with the fact that the curve neighborhood always wants to be bigger than the variety itself, right? So if you have a variety and if you want to travel with some rational curves from some variety, then of course you're going to grow up. But if you grow up, you either increase dimension or you decrease codimension. So this U of D means is the lower version. That means that the dimension is increases, and U of minus D, that corresponds to the decrease in codimension. So I'm defining these two elements. Question? Yes, I will tell you what it is. Yes. Yeah. There will be a theorem. So now I'm telling you essentially how to find, I'm defining the data. So I'm telling you that I'm trying to find what is this U of D and U of minus D. Okay? And once this U of D and U of minus D are defined, I'll just say that the 2-point Gromov-Witten invariant for O lower U and O upper V is just 1 or 0. Well, first of all, it's equal. There's a quantum equal classical statement here, a Gromov-Witten invariant of degree D using this cohomological triviality that Kevin asked about. This is gonna turn out to be the same as a degree 0 invariant, and this degree 0 invariant can be calculated using classical means. This is just an intersection of a Schubert variety and an opposite Schubert variety, and as we know, I think Alan mentioned this. This is just a Richardson variety. So you just look at when the Richardson variety is non-empty. And if the Richardson variety is non-empty, its Schiffer characteristic is equal to 1. If the Richardson variety is empty, it's of course equal to 0. And the non-emptiness is detected by the Bruchau order, with perhaps the opposite conventions, but that's what he mentioned. Yes. This is, of course, it's used in that proof, yes. So in particular, you can also find this this minimum degree that shows up in the quantum product in some combinatorial way once I tell you what this U of D is. Is the minimal D with the property that V is less in the Bruchau order than this U of D. So once you know what U of D is, you'll know what the minimum D is. And finally, I have this thing that I mentioned before. So if you want to pair a Schubert variety by a dual class, you always get 0 or 1. Again, using this quantum equal classical type phenomenon. So okay, so let me tell you how I calculate curved neighborhoods. So there are two methods. One is the moment graph method, and the other one is maybe I'm going to call it the combinatorial method. So the moment graph method is a method that has been used even outside the realm of homogeneous spaces. So people calculated curved neighborhoods just using the moment graph. So what is the moment graph? The moment graph, it's a graph which has vertices and edges. The vertices correspond to the elements, to the minimal length representatives of elements of W upper P, the T fixed points if you want. So the vertices correspond to the T fixed points in G mod P, and the edges correspond to the T stable curves that connect two such T fixed points in G mod P. Now a T stable curve exists exactly when one of the Weyl group elements is obtained from the other one, from U, by multiplication by a transposition. Okay, so when you have V obtained as U times Ij. Now every time when you have an edge, you associate a degree to it, because you think of an edge as a T-stable curve, so you want to say what's the degree of that T-stable curve. And that degree, of course, could be a multi-degree, could be just, if you have just one, the rank is 1, then you just have 1 degree. That degree is the degree of a root modulo delta P. So I'm going to discuss this in the full flag manifold. I don't want to say it. If you know that language, is going to be easy to translate. So I'll just say it in the full flag manifold in the Grassmannian in a moment. So, and then the theorem of Anders and myself is that the curved neighborhood has the Weyl group element, which is the unique maximal element in the Bruchau order, which is obtained from paths starting from U and traveling up in the Bruchau graph with degree less or equal than D. So I'll show you an example in a moment. So here's the moment graph for FL3. In FL3, there are 6 fixed points corresponding to the 6 elements in S3. These fixed points are joined by edges. In this case, we have by degrees, because we work in FL3. The rank of H lower 2 of FL3 is equal to 2, so we have by degrees. If you want to travel from the identity to S1, the by degree is, this is S2 in fact, from the identity to S2, the by degree is 0, 1. If you want to travel from the identity to 1, 0, the by degree is 1, 0. All these edges have by degrees here. There is also a big happy edge that goes all the way to the top. That has by degree 1, 1. So what is the procedure saying? The procedure is saying the following. Let's say that I'm interested in calculating the curve neighborhood of a point with a particular by degree. So let's say 1, 0 in this case. So if I want to calculate this curve neighborhood, I should start from a point. Okay, I should start from a point and I should travel with this by degree from that point. Where can I go? Well, if I start from the identity, I cannot go to this direction because this is degree 0, 1. I cannot go this direction because that's a degree 1, 1, so which is bigger than 1, 0. So I can only go here. And then because I cannot go any further, that means that the curve neighborhood of the identity, which is the class of the point in this case, it's exactly the Schubert variety corresponding to this S1. In fact, it's a Schubert curve. Similarly, if I have the by degree to be 0, 1, then the curve neighborhood corresponds to S2. Oh yeah, then I'm gonna go, if I start with S2, I can go here. I'm gonna go all the way to the top with 1, 1. Because I can go, it's not like a unique edge. It's a sequence, a path, it's a chain. Yes, thank you, indeed. It's a chain of curves, right? It's a chain of curves and the degrees just add up. So the degree of the path, no. So it's, for here if I take a degree which is very large, I'm gonna reach the top and just stay there. So in general, I'm allowed to travel by a path less or equal than that degree. And then if I reach the maximum, I'm gonna stay there. It's not clear from this description that there is a unique maximum. So actually this is a very good question. It's not clear that there is a unique maximum. The geometry tells you there is a unique maximum because it has to be a unique Schubert variety which dominates everybody else. But this procedure will always achieve a unique maximum. Yes. This is that's in the combinatorial method. Yes. Maybe I'll show you in 2 slides. So let me do it for the Grassmannian first. So this was the moment graph method. This is the combinatorial method. So here what I want to do is I want to do the curve neighborhoods for Schubert varieties in the Grassmannian. So what you do is you either add maximal rim hooks in case you want to increase dimension, or you remove maximal rim hooks in case you want to decrease codimension, right? Because the curve neighborhood is always growing as a variety. So here I have the partition is 3 to 1. I'm looking at the curve neighborhood corresponding to lambda of 2. So in other words, I'm looking at all the curves of degree 2, which pass to this Schubert variety of dimension 6. And I'm looking how far I can get inside the Grassmannian. So what's the Schubert variety? So this is now indexed by dimension, so the dimension has to grow. I have to have more boxes. I'm just adding 2 maximal rim hooks. And these are with red and yellow. And you can imagine what happens in general, right? And if I want to work in the codimension convention, I'm going to remove maximal rim hooks. And now I'm going to give you the general rule. So how you calculate curve neighborhoods for general flag manifolds? There is a recursive procedure that says the following thing. So I'll say it and then I'll explain. So the idea is the following. You first calculate curve neighborhoods for a point, and you get a particular Weil group element. Out of that, you can get the curve neighborhoods for any other Schubert variety. So you need to know how you do it for the point first. So let me explain first how you do it, how you do it in general, and then how do you do it for the point. So you'll need this notion of the Mazur product. So this is a particular operation on the Weil group, which gives the Weil group a structure of a monoid. So you take 2 Weil group elements, and you want to multiply them. First, I'm going to show you how you multiply by a simple reflection. So when you multiply by a simple reflection, you either multiply by that simple reflection if the length increases, or you stay where you are if the length decreases. Which is kind of what happens with the curve neighborhood. Once you reach a point, you never come back. Like the curves, once your curve neighborhood increased, it will never decrease. Okay, so the Mazur product is kind of like well suited for this, like how this curve neighborhoods behave geometrically. All right, so in general, if you don't have a simple reflection, but perhaps you take a word which has a reduced decomposition, so product of a simple reflections, then you can define u times v as just applying this recursively. And it turns out this is going to give a structure of an associative monoid. So, okay, so we define this element called ZD, which is the element that indexes the curve neighborhood of a point. So this is a particular Schubert variety that essentially consists of all the curves in the flag variety that pass to a point, all the curves of degree d or less that pass to that point. So then we have the following algorithm to calculate any other curve neighborhood. So if you take any other curve neighborhood, so gamma d of xu, then you just have to take the Mazur product or Hecke product of u by this element zd. So now I have to tell you how you calculate zd. So zd can be calculated recursively. You do it in the following way. You take, so this is a degree. So we've seen in Frank's lectures that degrees correspond to, well, in this case, it's roots or co-roots are the same in Lie type A. But it's good to think about them as co-roots. So you pick the maximal positive co-root, you should have in the co, with a property that that is less than d. And then there is a recursive procedure that says that zd is equal to the de Mazur product of zd minus alpha check Hecke or de Mazur with the transposition corresponding to that root. Okay. So in particular for ij, this would be the reflection. It's just if the root is ei minus ej, this is just the transposition that exchanges I with j. Okay, and there is a similar procedure for any G mod P. Yes. So if you let's work in the let me do it here. Let's work in FL3. Right, so you have to write all the roots in FL3. So you have to look at H2, H lower 2 of FL3. So this has two Schubert curves corresponding to 1, 2, and then 1 corresponding to 2, 3. Sorry. Okay. So we've seen in Frank's lecture that this corresponds to the root, to the co-root. Or root, in this case, it doesn't make a difference. In this case, this is just E1 minus E2, and this is E2 minus E3. Okay? But there are actually three roots, of course, for FL3. So FL3 can be written as SL3 modulo B. So there are three positive roots. The roots are just E1 minus E2, E2 minus E3, and E1 minus E3. In terms of the by degrees, they correspond to the by degree 1, 0. This corresponds to the by degree 0, 1. This corresponds to the by degree 1, 1. Why is 1, 1? Because this is written as E1 minus E2 plus E2 minus E3. So now if you give me a general by degree, D1, D2, can be written as a combination, right? It's like D1 times 1, 0 plus D2 times